Welcome to the Introduction to the Quantum Chemistry playlist. So, quantum mechanics is going to be studied very heavily in this course, and that is as opposed to classical mechanics. So, classical mechanics are the laws of physics that are used to describe the behavior of everyday size objects. So, you're familiar with Newton's laws, you're familiar with how everyday size objects like cars and boats and people, how those move with the various forces that act on them. So that's all classical mechanics. That's the kind of thing you learn about in introductory general physics courses. Quantum mechanics, by contrast, are the laws of physics for very, very small objects. So this is critical in chemistry because the scale at which quantum mechanics becomes important is the scales at which electrons, atoms, and molecules exist. So to compare and contrast these two laws of physics, you have classical mechanics versus quantum mechanics. Classical mechanics describes objects that are very large. Quantum mechanics describes things that are very small. Classical, things that are heavy, versus quantum, things that are very, very light. Atoms, molecules, and electrons are all very light compared to things like people and dumbbells and anything that would have a mass that you could reasonably measure in kilograms or grams or anything that you could touch, any macroscopic object. Classical mechanics is continuous, meaning that you can have very, very small changes in all of your quantities. So I can change the position or velocity or any energy, momentum, lots of properties of whatever object I'm interested in. They can change in very, very small amounts. By contrast, we'll see in quantum mechanics that the behavior of these objects is discrete. It's what you would call quantized. That's the root word of where quantum mechanics comes from. So discrete meaning that there are a finite number of states that a particle can exist in. It can't change its energy by any tiny value. It can only have certain allowed values of energy. So for classical mechanics, you would solve Newton's equations, things like force equals mass times acceleration, Newton's second law. And in quantum mechanics, you use the Schrodinger equation, which we'll derive several videos down the line from now. So when you solve Newton's equations, what you get is a trajectory. Your particle starts at a certain position, and it starts at with a certain momentum or velocity at an initial time. And solving Newton's equations, F equals ma, you get a trajectory of where that particle moves over time. Maybe it moves in a circle, maybe it moves in a straight line, maybe it accelerates, but at any point in time you know its position and its momentum. By contrast, in quantum mechanics, you get a wave function. The Schrodinger equation gives you a wave function, which isn't a map of where the particle is at any point in time, but it describes the particle as a wave. So the wave is spread out over space, and it doesn't have necessarily well-defined values for what its exact position is, what its momentum is. The only defined value that's going to be more well-defined will be probably the energy. For classical mechanics, it is what we would call deterministic. If you start with the same initial conditions of the same initial position and initial velocity, you'll get the same answer every time. And if you solve the equation again or do the experiment again, you should get the same result within whatever experimental error you have. For quantum mechanics, it's what we would call probabilistic. So if we have two systems in the exact same state and we make a measurement for both of them, they might not give the same result, but there are probabilities for what result they will give. Those probabilities for how it's going to behave is given by the wave function. The wave function tells us about the probability of various possible outcomes, but it doesn't tell us exactly what outcomes will occur in the same way that a classical trajectory would. And classical mechanics would be intuitive. We have a sort of intrinsic understanding of how classical mechanics works. We're very familiar with how everyday objects behave. We know that if you drop a ball, it'll fall to the earth and it'll accelerate while it does so. We know, how to throw things, how to catch things, how to keep things from falling over. We know how to build airplanes that fly. We know how to build cars that turn the correct direction. We're familiar with how all of these objects behave. Quantum mechanics is usually non-intuitive to us and has a lot of features that you wouldn't have guessed before you learn about how the Schrodinger equation and how wave functions work. And that's because we're just not familiar with how things work at this very, very small scale. So things like atoms, electrons, molecules are going to behave differently than everyday size objects are, and that's because of this quantum behavior. This quantum behavior is coming into play at very, very small scales, and it's very different than anything that we have experience with in our everyday lives. So that is the basic intro to quantum chemistry. This course is, the core of it is approximately 120 videos organized into about 10 chapters. Links to those in the description. They're organized into a course playlist as well as various chapter playlists. So if you're looking for specific topics, you can look in the entire course playlist, or you can look in the links in the description to the various chapters and the topics within those chapters. So as I said, I'm trying to organize this channel to be as easy to navigate as possible. So if you have trouble finding things, you should be able to search on the channel page, on the playlist page, or even in the YouTube search bar. The results seem to be pretty good for things. So let me know if you have any trouble with anything, any comments you have. I'm interested to hear definitely any feedback or any suggestions you have. You're welcome to send that in comments or by email as well.